welcome to the 61st lecture in the series. So towards the end of the last lecture, I talked a bit about this, the important operation called exterior differentiation on differential forms. So the formal statement is that there are unique linear maps from omega to omega k plus 1, so that when k is 0, we define 0 forms to be C infinity functions. So this df, this d that we are defining is the same as the usual derivative. And then there's a sort of Leibniz rule here. Then this mysterious property that d compose with d is 0. And then one has 3 additional properties which are that in a chart this d is given by this formula here like this, and d is local and restriction. Now all this might make d seem a bit abstract, but the key lies in this local expression for d. So in fact, let's use that first to talk about d in Rn. So d on open sets U and Rn. So let's take a k form. I know that I can write it as aj dxj, where the aj's are C infinity functions on U, and so let's define d omega equal to daj wedge dxj. Now why do we define it this way? Well, if we want the second property and the third property to hold, this is pretty much forced on us, because if I start with d omega of this form, then d omega, and of course I also need d to be linear. So d omega would be sum of d of these terms. D omega is sum d aj dxj. Then if I impose the Leibniz rule condition, I would get d aj wedge dxj plus the daj wedge plus minus 1 to the power k aj wedge. Now this is a function, so function at a point is just a constant, so wedge is just usual multiplication. So aj times d of dxj right, and well, this dxj is what we mean by dxj is the way was dxj1 wedge dxjk. This was dxj. So if I take d of this, I will be taking d of this right hand side, and I will be using the Leibniz rule many times. So I'll get lots of, I'll get exactly k terms if I apply Leibniz rule. But in each term, for example, the first term would be d of dx j1 wedge. The remaining stuff would remain, remaining terms would remain the same. Dx jk plus dot dot dot. You'll get signs also, and in each term you will be doing d of some dx, some index. Now the second condition tells us that d of d is 0. So here I have d of d, and actually I am using the first condition as well. In the first condition tells us that the d which is occurring here, by the way, is the classical interpretation of derivative of a smooth function as a one form. This d that I am writing is the new operation d. So but this old d and new d coincide. So d composed with d is 0. So all these terms will be 0. So this entire thing goes away. So I am left with daj wedge dxj. In other words, if we impose linearity condition 1, condition 2, condition 3, this is pretty much the only possible definition of d omega. Now let's look at it a bit more carefully. This is what we have here. First let's try to see what is if f is from u is a C infinity function, df we know is a one form. So but what are its and any one form can be expressed in terms of dx1, dx2, dxn. So when we do that, what are the coefficients? I claim that then df is equal to summation del f by del xi dxi. And this is quite clear, because all one has to do is, it's the same old way of getting hold of the coefficients whenever we have an expansion like this. If df is equal to some, let's say, bi dxi, then df evaluated on del by del xj is this bj. All the other things will be 0. So but this is the same as del f by del xj. Right, so one gets this. Yeah, so therefore one has this expansion. So all the coefficients are just partial derivatives, and one has this. So going back to this and plugging, instead of f, of course here I have aj's. So therefore d omega I can write as summation over j summation over I del ai del aj by del xi dxi, and then wedge dxj. So let me remove this two summations and just put summation over I and j over I comma j of this thing here. Now let's see what we get when we have a one form. So these are examples actually. if omega is a one form, actually in this example, if f is smooth, so okay, so this is just a simpler way. It's not really an example, but let's now, this is an example. If omega is a one form, then we know that then I can write omega as aj dxj, and then d omega would be going by the stuff that I have here. So this is summation over j, summation over I comma j, del aj by del xi dxi wedge dxj. Now, if I equals j, I'll get dxi wedge dxi, which will be 0 because of the anti-commutativity property of one forms. So I have to consider two cases: I less than j, del aj by del xi dxi wedge dxj, plus I greater than j, del aj del xi dxi wedge dxj. Now the second thing, I'll just interchange the indices and write it as I less than j, del ai by del xj, del xj wedge del xi, and notice that this is the same as negative of dxi wedge dxj. Now I can combine these two terms, the first term and this term. So therefore equal to I less than j, here it's del aj by del xi, here it's del ai by del xi, but with a negative sign. So del aj by del xi minus del ai by del xj dxi wedge dxj. So this is the expression for a d of a one form. Well, that's just an example. And it turns out, interestingly enough, that there's a nice way of writing this without using coordinates. It turns out that this is true on a manifold as well. D omega, if omega is a one form, d omega is a, well, it's a two form, and its action on any two vector fields is given by x as a derivation acting on omega y, which is a function. If I take a one form and plug in a vector field, I get a function. So then I'll be differentiating that y omega x minus omega, the Lie bracket of x and y for all x, y, n. So this is only for one forms, and here one is not using coordinates. Sometimes this formula is useful. It can be shown that at any rate we haven't still defined it on a manifold. So let's continue with the D that we have here. Of course, one can check that this formula is valid for open sets on Rn as well. what I have here. But I really don't need this. So proposition. We already, so the point is we now have a definition of D on open sets, namely this. The expression inside the orange box is our definition of D. We claim that this D is linear, which is quite trivial. I won't prove that. The D satisfies this. D omega wedge eta plus minus 1 to the power k omega wedge eta d eta, where omega is a k form and eta is a L form. So let's the other thing is decompose in this, and the fourth thing is if f is a smooth map from U to V, smooth, then so U and V are open subsets of Euclidean spaces, not necessarily of the same dimension, they can be of different dimensions as well. F star d omega, this property will be crucial for going back to the manifold, for transferring everything back to the manifold. The first three properties anyway we want, it was in the theorem. Now here from what I have written here, so let's see. So if omega is for example a function, then I would get df wedge eta plus f wedge d eta. So that's fine, zero form. So right, so this is correct. So in the previous theorem, I think I interchanged the role of, so I should actually want a small change here. This is the other way around. So this is omega is k and this is L. So let's prove this. Proof. Well, one is clear, so I won't go into one. Now, as for two, we can assume that omega is equal to u dx I, eta equal to v dx j, where u and v are smooth functions. U, v are smooth functions on u. And the reason we can do that is we can just expand both omega and eta in terms of the basis of the space of K forms and L forms, and we can do that on this left hand side and right hand side. The coefficients that we get will be the same. Well, not quite, the coefficients will not be the same, but we can just expand them in terms of their basis, and then use multilinearity of this wedge product operation and then so on. So I won't go into details. Maybe it's quite it's a straightforward and can be a topic for the tutorial. So we have this. So let's work with these two forms of this type. First, note that d of u dxi is du wedge dxi even if I is not increasing. The way we define d, everything here, the index j here was an increasing index. So when we have an increasing index, and then we had this formula. But here what we are claiming is that it's same thing is true. Even if I don't have an increasing index, I still get this. And it's quite simple to see this, because as usual, if something is not a strictly increasing index, if I has repeated indices, then both sides are 0. So that's a trivial case. Again, so let me make a comment here. If I has repeated indices, then both sides are 0. So why is this the case? Well, more general comment is, after all, what is dxi? This is by definition dxi1 dxik. So more generally, let's look at omega 1 wedge omega k, where this omega i's are 1 forms. The claim is that this expression is 0 if omega I equal to omega j for some I not equal to j between k and 1. So if these indices, two of them coincide, so then a wedge product will be 0, and one can see this in a couple of ways. One is we already had a nice expression for what this is when we are talking about the vector space setting. We know that this is det of omega I vj. And if omega I equal to omega j, then two columns of this matrix, two rows of this matrix will be the same. So therefore the determinant will be 0 no matter what v1, v2, vk are. So one gets this, or one can also see it using the anti-commutativity property of the wedge product. So here, coming back to this, if I has repeated indices, then some dx, some index will be equal to dx with some other index. So therefore the wedge product will be 0. The other possibility is that otherwise all indices in I are distinct, but they may not be in increasing order. Let sigma be the permutation sending I to j, where j is in increasing order. In other words, rearrange the indices so that they are in strictly increasing order, and call that rearranging permutation sigma. So then what will happen, so we are interested in duxi is the same as, so once we do that, dxi, which is this, will be, as we have seen before, sine sigma dxj. So therefore this will become sine sigma u, so instead of dxi I just put dxj. So the d will still remain dxj, and well, sine sigma. Now the point is, this j is in increasing order, so d of this I know by definition will be du wedge dxj. Again combine the sine sigma with dxj to get dxu dxi. That's it. So this shows that this formula continues to hold even when now we'll need that, because now let's start calculating this. So you take omega and eta, and let's calculate this d. Now omega I assumed is u dxi, and this is v dxj. So I'll get uv dxi wedge dxj now immediately I'll use this the previous remark that the formula this formula holds whatever the index is. So this dxi wedge dxj we know is the same as dx ij, where ij is the concatenation of I and j. So we can use the formula to conclude that this is duv wedge dxi wedge dxj. I might have written it as a dxij, but I'll keep it like this. Now again use the Leibniz formula here to get u dv plus v du wedge dxi wedge dxj. So let me quickly complete this, and then so I can combine this and write it as u so this u dv, so this term v du will give rise to du wedge dxi. So I'm combining these two, wedge v dxj. So this v I'm taking to here, plus here's where the negative sign is coming from, minus 1 raised to k u dxi, well right, so I'm starting with this, and then the dxi I'm moving past the dv, and dv wedge dxj. The dxj remains wherever it was. So because I interchanged dxi and dv, I got this minus sign, minus 1 raised to k, and this is the same thing as d omega wedge eta plus minus 1 to the k. After all, this is eta. This thing here is eta, this is d omega, and so this is omega wedge d eta. This is d eta. So that proves the second property. So we'll stop here. In my next lecture, I'll deal with the other two properties. Then we'll see how we can transfer all this to the manifold setting. Okay, thank you.